Dear students, due to COVID-19 situation, you cannot attend the laboratory experiment. Through this video, I am trying to bring a real laboratory experiment up to you. So, watch full video, record the reading during the experiment and perform the calculations. In this experiment, we will explain and perform conductometric titration between weak acid, acetic acid and strong base NaOH. Furthermore, we will explain setup for conductometric titration and how to locate end point of the titration by conductance measurement. We perform the titration, and in the titration we add indicator to indicate endpoint. For example, we have the titration between acetic acid and NaOH. We use phenolphthalein as indicator. At equivalence point or near to the equivalence point, phenolphthalein gives rise color change. For example, we have taken acetic acid in flask, titration flask, and NaOH is added from the burette. Then end point is colorless to pink, okay. Now the same titration can be carried out by conductance measurement. So when titration is performed, by conductance measurement, and end point is obtained from the conductance measurement, then titration is called as conductometric titration. Conductometric titration. So the titration is same, only the methodology by which the endpoint is obtained is different, and here the endpoint is obtained from the conductance measurement. Okay. Now the same example we have acetic acid and the NaOH, how the titration can be performed. Acetic acid is taken in a beaker. Okay, we have a beaker, and in a beaker acetic acid is taken. Suppose we have the approximately 0.1 molar and 50 ml. Burette NaOH is filled. Burette NaOH is filled, and NaOH is exact 0.5 molar, 5 times higher concentration than the acetic acid. This is the requirement for the conductometric titration, so that endpoint can be obtained very accurately. Okay, so what is done? The conductivity cell is placed in the acetic acid solution and the conductance is determined. When NaOH is not added, conductance is determined. Then 0.5 ml NaOH is added at a time. Okay, so 0.5 ml NaOH at a time. The solution is stirred on the magnetic stirrer and the conductance is determined. Okay, so by this way the number of readings are taken till you will get the breakthrough in the readings or in the conductance of the solution. Okay, so this is the methodology for the conductometric titration. Now what is the theoretical basis and how the end point is obtained? Okay, so we have acetic acid CH3COOH. It is weak acid and it dissociates to less extent, forming CH3COO minus plus H plus ion. So initially when we take the 50 ml solution of acetic acid in a beaker, it shows some conductance, and it is due to the presence of small quantity of acetate anion and H plus ion in the solution. Now we have added NaOH from the burette. What will happen? Acetic acid will react with NaOH and we get sodium acetate CH3COONA plus H2O. But if you see now, sodium acetate, it is a salt and it dissociates completely, forming CH3COO minus plus Na plus ion. So when we add 0.5 ml NaOH every time, what will happen? The quantity of acetate anion and Na plus ion goes on increasing. That is, the quantity of anion and the cation in the solution increases. Thus what will happen? As quantity of ions increases, the conductance increases. Conductance increases. Thus, the conductance of solution will increase constantly and continuously up to the equivalence point. Okay, since every time we are adding 0.5 ml NaOH and we get the respective amount of acetate anion and the Na plus ion, and hence conductance will increase up to the equivalence point. At equivalence point, there is no acetic acid. Why? At equivalence point, all acetic acid is consumed from the flask. As a result, what will happen? After equivalence point, added NaOH will be in excess. NaOH is a strong electrolyte. It dissociates completely, forming Na plus ion and OH minus ion. So after equivalence point, the quantity of Na plus and OH minus increases, and it will increase continuously with every 0.5 ml addition. Now, if you see the Na plus ion before and after equivalence point is common, what is different? OH minus ion and acetate anion. After equivalence point, acetate anion is replaced by OH minus ion and quantity of OH minus increases continuously. So if you compare the conductance of CH3COO minus ion and OH minus ion, conductance of CH3COO, conductance of acetate anion is low and conductance of hydroxyl ion is high. Why this is so? Since acetate anion is larger in size while OH minus ion is smaller in size. So the movement of OH minus ion or the velocity of OH minus ion in the solution is high and hence it shows high conductance. Thus what will happen? With every 0.5 ml addition of NaOH after equivalence point, the increase in conductance is large. Suppose before equivalence point, increase in conductance is by 0.03 unit. Then after equivalence point, it will be around 0.06 to 0.08 unit. That is, after equivalence point, you will get the breakthrough in the conductance. That is, increase in conductance with every 0.5 ml addition is large. Okay, and this is the basis for the determination of equivalence point. Then how equivalence point is determined? Equivalence point is determined graphically. The graph is plotted. Y-axis conductance, x-axis ml of NaOH. Conductance, it is in the millisiemens unit. Okay, so if you plot the graph, just first put up the point, you will get the point like this. Okay, then you have to draw the two straight line. First and second. So these two lines intercept at this point. Put up a perpendicular to the ml of NaOH, that is x-axis. Here you will get end point of the titration. Okay, so you have to obtain end point of the titration graphically. Now the calculation, they are very simple one. So you are familiar with the equation m1 v1 is equal to m2 v2. So what is known? m1 is known, molarity of NaOH 0.5, volume of NaOH obtained from the graph, that is end point of titration. m2 is to be calculated and v2 50 ml. So you will get m2 is equal to m1 v1 upon v2. You will get molarity, and from molarity you can calculate the strength. Okay, you can calculate the strength. Molarity into molecular weight. Okay, so by this way you can perform the titration and you can obtain the end point. Now what is the application or the advantage of the conductometric titration? Some of the titration can be performed. For example, we have the titration between Pb2 plus ion and SO42 minus ion. You will get precipitate of PbSO4. Thus lead can be analyzed by gravimetry as lead sulfate. But if you see the gravimetric procedure, they are very lengthy, time consuming and also energy consuming. It requires heating. This lead can be analyzed by the titration. But what is the disadvantage? The disadvantage is that for this titration there is no availability of the suitable indicator. No availability of the suitable indicator. Thus what could be done? You can perform titration by using the conductometer and you can obtain the end point of the titration. So though there is no availability of the indicator, the conductometer can be used to identify the end point. This is the advantage. So some titrations are possible where indicator is not available but conductometer can be used, conductometric measurement can be used, and you can identify the end point of the titration. While watching the video, write down burette reading and the conductance so that you can perform the calculations. Now we will perform the conductometric titration between NaOH and acetic acid. I have taken acetic acid in a beaker and I will put up this acetic acid on a magnetic stirrer so that solution can be constantly stirred during the experiment. I will dip conductivity cell properly into the beaker or into the acetic acid solution. Okay, this is magnetic stirrer. This is now 50 ml 0.1 molar acetic acid solution. This is conductivity cell and this is microburette in which 0.5 molar NaOH is filled. Now I will put up the conductometer and the magnetic stirrer on. Okay, so conductometer and the magnetic stirrer is placed on. Okay, so first of all we have to carry out the standardization of the conductometer. I will put up this switch on, which is for the standardization of conductometer. Okay, I will select 2 ms range, 2 millisiemens range, and under this condition conductometer should show the reading 1.000. Okay, so you can rotate this screw and you can adjust the conductivity. Okay, so it is 1.00. So setup is ready to perform the titration. Okay, so I will select the range of the 20 ms to perform the titration. So for 0 ml reading, for 0 ml addition of NaOH, reading is 0.55. Now we'll add 0.5 ml NaOH from burette. The stirrer should be placed on. Okay, so the reading is 0.61, 0.5 ml 0.61. Now next 0.5, that is 1.0 ml, reading is 0.93. Then next 0.5, total volume is 1.5 ml, reading is 1.31. Now 2.0, 1.68, 2.5, 2.03, 3, 2.36, 3.5, 2.69, 4.0, 3.00, 3.31. So we have 5 ml reading, 5 ml NaOH is added, reading is 3.62, 5.5 ml now, 5.5 ml, 3.94, 6.0, 6.0, 4.24. So we have to perform the titration till you will get abrupt change. So if you see up till the difference between two reading is around 0.3. Okay, the difference is around 0.3. So when we will get the difference around 0.5 or 0.6, we have to stop the titration. We have to stop the titration. So the next reading is for 6.5 ml. 6.5 ml. The reading is 4.53. We have 7.0 ml reading now. 4.78. 7.5 ml, reading is 5.04. 8 ml, 5.34. The difference is still 0.3, so we'll continue the titration. 8.5, 5.59, 9.0, 5.82, 9.5, 6.09, 10, 6.34. So we will fill up the burette once again. So we have filled the burette once again. So we will start with the reading 10.5, 10.5, 6.57, 11, 1.5, 7.04. Now 12 ml as such, 12 ml, 7.48, 7.5, 8.34. Now you can see the difference is very large and difference is around 0.9. So we have to take 3-4 reading till. So 13 ml, 9.04, 13.5 ml, 9.74, 14 ml, 10.53, 14.5, 11.23, and we'll take the last reading for the 15 ml. So 11.82. Okay, so we have completed the reading. As per the instruction given, you have prepared the table of conductance against ml of NaOH. Now plot the graph as explained earlier, find out the endpoint of titration and calculate molarity and the strength of acetic acid.